welcome to our class. Today we are looking at vectors and scalars, and we begin with a few definitions and then look at examples. So first we define a vector and say that a vector is any quantity that has a magnitude and direction, and the examples of vectors are displacement, velocity, acceleration, and force. Now, how do we represent a vector graphically? This is a vector. It's just a directed line that has the origin and where it's going to. So this is our terminal point. So this vector OA, where O is the origin, where it's coming from, and A is the terminal point. So analytically, to represent a vector A, we represent with A with an arrow above it. An arrow above it, so that means it's a vector. And the magnitude of this vector, we represent it by this. So this means the magnitude of A. So I'll say that a vector can also be represented analytically by this, A with an arrow above it, and its magnitude will be represented by this. So this is a magnitude of vector A. In printing, you can print boldface like this. It means vector A, and its magnitude can be printed this way. That is if you are printing. And they mean the same as what you already have. They mean the same as vector A and the magnitude of A. Now, in this course, in our class today, we'll combine the two. In some cases, we'll be using boldface, and in some cases, we'll just be using an A with an R above it to mean a vector, and then an A with an R above it with these two parallel lines to mean the magnitude of A. So where we have OA, and then we will represent this to mean vector OA, and its magnitude will be represented by this, the magnitude of vector OA. We can also define a scalar, and we say that a scalar is just a quantity that has only magnitude. It doesn't have direction. So the examples of scalars are mass, time, length, temperature, and even real numbers. Real numbers are scalars. Now, the other definition, we want to define equal vectors. And we are saying that vectors, two vectors or more vectors are equal if they have the same magnitude and direction. For instance, look at figure 2. Figure 2, our vector P and vector Q are equal vectors because the magnitude are equal and the direction also equal. So the magnitude, we just looking at the distance from this point to this point is the same as the distance from this point to this point. That is the magnitude. And then they are also facing this direction. So these two vectors are equal. And look what these other two vectors. They have the same magnitude, yes, but their directions are not the same. They are not facing the same direction. So the two are not equal. But what we can see is that vector P equals negative vector Q. Vector P and negative vector Q are equal because they have the same magnitude. It's only their direction that is different. So this negative means their direction are not the same. They're not facing the same direction. That's why I've said here that if a vector P and vector Q have the same magnitude but different directions, then Q will be equal to negative P. And this is illustrated in figure 3. This figure 3. Now I want us to look at components of vectors. But just before that, let's define a few terms and then we look at components of vectors. I want to define a null vector. A null vector, and that is a vector whose magnitude is 0 and it has no specific direction. That is a null vector. We represent it by 0, vector 0. We can call it null vector or 0 vector. Any other vector that is not null is said to be proper vector. So in our case, all the vectors, unless stated otherwise, will be proper vectors. A vector with the magnitude of 1, a vector of unit magnitude, is called a unit vector. So its magnitude is 1. Now, if I'm given vector A and I'm asked to find a unit vector in the same direction as this vector A, I'm given vector A and then I'm asked to find a unit vector in the same direction with vector A, what I would have is I will take vector A divided by its magnitude. Vector A divided by its magnitude. The result is a unit vector which points in the same direction as vector A. That's what I've written here. I've said that let magnitude of A be the magnitude of vector A. Then a unit vector in the direction of A will be given by this. There's a unit vector in the direction of A. Now let's look at components of vectors or vector components. I've said, point 1, that any vector A in a plane is described by a pair of its vector coordinates. So for example, if I can have vector A and I will say that it's 2, 2, 3. This is just a coordinate. This is just a coordinate where vector A is. So in two-dimensional space, the x-coordinate of a vector, I'll denote it by this. The x-coordinate of a vector, I'll denote it by vector A. This is vector A. So I'll denote the x-coordinate of vector A as A1I. And denote the y-coordinate of vector A as A2J. That's how I want to denote them. That's how I want to denote those x-coordinate and the y-coordinate. For example, in this A, this is my x-coordinate and this is my y-coordinate. Now this x-coordinate of A, we call it the x-component. And the y-coordinate of vector A, we shall call it the y-component. The y-component. So that vector A shall be the sum of these two components. Shall be the sum of the x component and the y component. This is in 2 dimensions. Likewise, in 3 dimensions, vector A shall be the sum of A1I plus A2J plus A3K. Now let's look at this figure 5. So this is my vector A. This is vector A. Its x component is here and its y component is here. because vector A, this is the origin, and it goes up to this point. So you can see that we have the x component and the y component for this vector. Now what is important to this is that they form a right angle triangle. It forms a right angle triangle. This angle here is 90 degrees, and that we can use trigonometric ratios here to express the x component and the y component of this vector. So they can be expressed in form of trigonometric ratios. For instance, if you are to look at this angle theta, then cos theta, which is adjacent over hypotenuse, would be the x component over, that is the magnitude. This is the distance from here up to here. The distance from here up to here is magnitude of this x component. So the magnitude of the x component over the magnitude of the vector, that gives me cos theta. So that means this x component of A, the magnitude of this x component can be expressed in terms of trigonometric ratio as magnitude of vector A times cos theta. Likewise, sin theta, which is given by opposite over hypotenuse, our opposite to theta is that, hypotenuse is that. So this distance over this distance gives us sin theta. And that's what I've written. Sin theta equals to magnitude of the y component over the magnitude of vector A. And this implies that this y component can be written as magnitude of A times sin theta. So I have this equation 1 and equation 2. So what follows is that let's now square this and then square this and add the two results. So when we square those two equations and add the two results, the left side I'll have the magnitude of x component square plus the magnitude of y component square. That's what I have, these two. And then squaring this part, I would have the distance of A square cos square theta. And then again, this magnitude square sin square theta. So this is what I have. At this point, you realize that this is common, so you can factor it out, and you would have magnitude of A square into cos square theta plus sin square theta, and this equals to 1. This equals to 1. So the right side becomes the magnitude of A, vector A square. So what do we have? What we have is the magnitude of the x component square plus the magnitude of, this is supposed to be 2, the y component square equals to the magnitude of vector A, again square. So that means I can get the square on both sides, and if I was to get square root on both sides, this is what I arrive at. I arrive at that the magnitude of vector A equals to the square root of the magnitude of x component square plus the magnitude of y component square. And again, this is 2. This y component. Therefore, the magnitude of vector A in two-dimensional space will be given by this. And in three-dimensional space, we would have it this way. So that means if I'm given vector A as 2, 3, where this is the x component and this is the y component, it's easier for me to get the magnitude of this vector by just saying that it's the square root of the x component square plus the y component square. So it's very easy for us to get magnitude of vectors. And that's what I've stated here and said that given x, y, and z, these are coordinates, and then its position vector r will be given by this. This is a position vector for this. So you see, if I have, this is my origin, and I have r, and this coordinate is x, y, z, is a coordinate here. Then the position vector of this r will be given by xi plus yij plus zk. That's what I've just written here. What about the magnitude of r? The magnitude of r, as we already stated, would be the square root of x square plus y square plus z square. And that's what we have here. So let's look at a few examples. Given r equals 2i minus 3j minus k, and r2 equals to 2i minus j plus 2k, and r3 equals that, find the magnitude of r2. So let's just do that. The magnitude of r2 will be given by the square root of, this is our r2, so the square root of 2 square plus negative 1 square plus negative 2 square. So this is, in fact, it's the square root of 4 plus 1 plus 4, which is 3 units. Is 3 units, because this will be 9. So the square root of that will be 3. Now, so I'll do this, then I leave this as exercise. So let's try and do that. We just clear this part, and then we'll use it. Okay, so we're supposed to do R1, R2, R3 and get the magnitude of that. So let's add. R1 is 2i minus 3j minus k. R2 is 2i minus j minus 2k, and R3 is negative 3i plus 2j plus 4k. So collecting like terms, we have 2i here, 2i, another 2i, that comes to 4i, then minus 3i, that gives us I. Okay, now the j's, we have negative 3j, then negative j, that comes to negative 4j, then plus 2j, that comes to negative 2j, because this was 4 negative, then plus 2. Then finally, negative k, then minus 2k, that comes to negative 3k, and then plus 4k, that comes to k, because this was negative 3 plus 4, which is 1. Now, so what we're supposed to get is the magnitude of this. And so this is same as the square root of 1 square plus negative 2 square plus 1 square. And this is 4, 5, 6. This is root 6. That's root 6. So root 6 becomes the magnitude. So as I said, you do part C as your assignment. Now, so what we said is that if you have this figure here, this figure 5, I've said to find direction of a vector, and remember this was our vector. This was our vector A, and its direction is this. This is its direction. So to find the direction of this vector A, what you just find is the angle that this A makes with the x-axis. So the angle that it makes with the x-axis is the direction of that vector. So that's why I've said that to find the direction of vector A, you just need to solve this tan theta, which equals to opposite over adjacent, where the opposite is the y component, and this adjacent is the x component. So you solve for theta. You solve for theta in this equation here. Let's look at an example. The magnitude of a vector is 6 units, while its direction is 30 with the horizontal. Find the components of the vector. Find the components of the vector. And you remember that we had said cos theta is the y component, not the x component, the x component over the hypotenuse, which is 6. And we would also say that sin theta is the y component over this magnitude, and we've been told this magnitude is 6. So that means that to get the x component, I only need to get 6 times cos theta, where theta is 30. That's why I wrote here. I say that the x component will be 6 times sine 30, and sine 30 is this. When you use the special angles, remember this triangle here, remember this triangle, this equilateral triangle, and this is 2, this is 1, this is root 3, this is 60 degrees, and this is 30 degrees. So that cos 30 will be adjacent over hypotenuse, which is root 3 over 2. And this gives us this as the x component. And then the y component is 6 times sine theta. Sine 30 is a half. So that gives us 3 as the y component. So that this vector can be written in terms of the x component and the y component like this. Or you can write it as 3i root 3 plus 3j. Let's look at another example here. So this example, we're supposed to prove something. And the question is, let M and N be two non-collinear vectors. You remember collinear vectors? These must be vectors that are parallel and they have a common point. They are parallel and they have a common point, or they are on the same straight line. They are on the same straight line. So let M and N be two non-collinear vectors. Then show that mx plus ny equals to 0 would imply that x equals to y and then equals to 0. So just want to show that if these two vectors are not collinear, in other words, they're not parallel and they don't lie on the same straight line, then the vector m times x plus vector n times y equals to 0 will imply that x is 0, y is also 0. So to prove this, we do by contradiction. So we assume the contrary. Assume that x is not equal to 0. Or we may also want to assume that y is not equal to 0 and see what happens. So I chose to assume that x is not equal to 0. So what will that mean? If x is not equal to 0, then it means this part is not 0. This part here is not 0. mx is not 0. So it means we can take this on the other side of the equal sign and have mx equals to negative ny. So dividing both sides by x, we would have m equals to negative n times y over x. What does this mean? This means that this vector m can be written in terms of n. Can be written in terms of n. And once a vector can be expressed in terms of the other, it means that the two vectors are parallel and that they lie on the same straight line. So that means m and n are parallel and therefore collinear. So you have seen that assuming that x is not 0 has made us contradict the assumption that we were given. The assumption here was that the two vectors were non-collinear. And when you assume that x is not equal to 0, you contradict yourself. You reach a conclusion that these two vectors are collinear. And so that means that this assumption here is not correct. The assumption that x is not equal to 0 is not correct. So that therefore means that x must be equal to 0. So if x equals to 0, we come back to this equation here. When x equals to 0, it means this part will be 0. So you're left with the ny equals to 0. So if ny equals to 0, dividing both sides by n, you discover that y will also be 0. Y will also be 0, and therefore you'll have shown that mx plus ny equals to 0 will imply that x is equal to 0 and y will also be equal to 0. Okay, let's look at another question and see how to prove it. Let m and n be two non-collinear vectors. Prove that mx plus ny equals to ms plus nt will imply that x equals to s and y equals to t. That's what we want to prove. We want to prove that if this equals that, and then x equals to s and y equals to t. So this one, the way I wrote it, I just took this one to the other side of the equal sign, so that I'm left with a 0 here. So that we have said that this can be written as mx plus ny minus this one taking the other side of the equal sign equals to 0. So I brought the like terms together, those that have an m together and those that have an n together. So factoring out m, you see, I have this and minus of this mx and minus ms as like terms. So if I brought them together, I would have m into x minus s. Then plus the same thing, I do it for n. I would have n into y minus t equals to 0. Then by this example, I already know that this part plus this part implies that this equals to 0 and this also equals to 0. That's why I say by this example 3, it means that this part, this constant here that I'm multiplying by the vector equals to 0, and this other constant here equals to 0. So what that means is that this constant here equals to 0, and this constant here also equals to 0. And that's what I wrote, that we have that x minus s equals to 0 and y minus t equals to 0. So if this is true, then it means that I can take this negative s the other side of the equal sign to mean x equals to s. And I can also take this t the other side of the equal sign to mean y equals to t. And we will have proved, we will have shown what we were supposed to show. Then let's look what this other example. Okay, this example says let A be equal to this. This is a vector equals that, and B is another vector which equals that, and then C is another vector, and then D's are also a vector. These are 4 vectors. We need to find scalars x, y, and z such that D can be written as a linear combination of the vectors A, B, and C. So you know that when we write a vector in terms of the other, we say that we've written as a linear combination of those others. Now, so what we need to do is just need to equate the 2 vectors, this vector on the left and the vector on the right side. So let's just do that. Let's begin with the right side. The right side says x multiplied by A plus y multiplied by B plus z multiplied by C to give me D, but D is 2i plus 3j plus 5k. So let's just multiply them out and then equate the like terms. I would have negative xi plus 3yj plus zi equals to 2i. Or I can do without the i's. I can say this is the same as negative x plus 3y plus z equals to 2. Doing the same for the j, I would have 2x plus y negative 2z equals to 3. Then lastly, I do the same for the k. I would have x minus 2y minus 3z equals to 5. This equation, we can solve it using various methods. You can solve it, you can even reduce it to, can eliminate one unknown, can use this to eliminate one unknown, and use this to eliminate one unknown. You are left with the two simultaneous equations and solve by either elimination or substitution. But I just want to do by reducing this to echelon form. I want just to reduce this to echelon form. Or I just want to use elementary row operations. We just use elementary row operation, but you can even use Cramer's rule if you want. Now, how to solve this? You can you can check my other video on solving systems of linear equations. How we solve this. So I'll use this element here to clear the elements below it in the first column. So I want this one to be 0 and this one also to be 0. So the first row remains where it is. The first row remains where it is. And to create a 0 in this position, I need to multiply this row by 2 and then add it to this row. So I need to multiply row 1 by 2 and then add it to row 2. So doing that, this by 2 added to this, I get a 0. This by 2 is a 6. Added to this, I have 7y. And then this by 2, I have 2z. Added to this, I have 0. This by 2, I have 4. Added to this, I have 7. Then I come to this. I want a 0 in this position. So you can see that I only need to add this to this, and I have a 0. So that means that I'll be adding first row to the third row. And so this plus this, I have a 0. This plus this, I have a y. This plus this, I have negative 2z. And in this, 2 plus 5, I have a 7. Now, but you can see from this equation 2, you can see from that equation 2 that y equals to 1. So if y equals to 1, then you can come to this equation here. You can come to this equation and see that z will be what? Just put 1 here. So z will be negative 3. Z will be negative 3. And then now proceed this equation here and substitute in y and z. So what we have is that x is equals to 2 minus 3y minus z. But we know what y is. We know that y is 1. We know that y is 1. And we also know what Z is. We know that Z is -3, and there's a negative here. So it's +3. So that X becomes 2. So X is 2. So the question wanted us to find the constants X, Y, and Z so that D can be expressed in this form, and we've just found those constants. Let's find those constants. So that is the end of our today's lesson. We'll have our next lesson on other topics in meta-analysis. We'll look at the dot product, cross product, and their applications.